Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will talk about the concept of independence. First, let me show you a theorem. This theorem has to do with a way of showing that two continuous random variables are independent. And something that we're going to see in the near future is that when you have independence, some probability calculations simplify. Okay. Another thing that we're going to be seeing in the future is that sometimes when random variables, are not independent, we would like to come up with a way, a numerical measure of how dependent they are. Okay, and that's why at some point again in the future we are going to be talking about concepts such as the covariance between random variables and correlation. Okay, but that's a different topic, a topic for another video. Anyway, so as I said, in this video we are going to be discussing independence, and there are different ways of showing independence between two random variables. This guy here, Theorem 5.4, is one way of doing so for continuous random variables. And what we have here is that if the joint probability density can be expressed as the product of, in this case, since we're just talking about two of them, if the joint probability density for variables y1 and y2 can be expressed as the product of their marginals, then y1 and y2 are said to be independent. Well, now, how about we do an example? Okay, let's do that one. Okay, as you can see, we have the joint probability density for x and y, and we want to determine whether or not they are independent. So let's use that theorem. What we have to do is we have to find the marginals of x and y. So in this case the joint is something simple, and again this and this, these two restrictions, if you will, these inequalities are going to be defining the whole support, the set of values where the joint PDF, the joint probability density function is non-zero. Okay, so we have the joint is 1/8. And we have that condition, x must be between 0 and 4. And we also have y must be between 0 and 2. Okay, and we have that the joint probability density function is 0 otherwise. Okay, so first let's find the marginal for x, or marginal of x. Marginal of x. Okay. So first, remember, by definition, okay, if you have two continuous random variables, if you have the joint probability density function and you want the marginal of x, what you do is you integrate the joint PDF with respect to the other variable. So by definition, what we do is just the marginal of x will be the integral from negative infinity to infinity of the joint probability function, well, joint probability density function, and we integrate with respect to the other variable. In this case, note that y is restricted to be in that interval, the interval that goes from 0 to 2. So we have the integral from 0 to 2 of our PDF. Our PDF is something really nice. It's just a constant, 1/8 in this case, with respect to y. Okay. So we're going to have something nice here by the linearity of integrals. We just factor that out. This is a1 clearly. Integral with respect to y of 1 is just y, right? So it's going to be 1/8 times y, but y will be evaluated here at 0 and at 2, no problem. And well, it's going to be easy, right? It's just going to be 2 divided by 8 in the end, which happens to be just 1/4. Now we need the support, the set of values for which that expression applies. Guess what? X must satisfy that. Okay? Now, take a look at this expression. It makes sense. Right now that we see it, we go, oh, I see. So 1/4 from 0 to 4. This is a continuous, uniform distribution, right? So immediately we know that this is a legit probability distribution. Okay, so now let's do something similar for the other one. We have the first marginal. Now let's find the marginal with respect to y. All we have to do is now, since we want the marginal of y, we just have to integrate with respect to the other variable, right? We have the joint. Now, since we want the marginal of y, we integrate with respect to x. Okay? Again, we have that constant, So it's going to be 1 over 8, but now we are going to be integrating with respect to x, and we have to bear in mind that this guy, right, goes from 0 to 4. Okay, x is restricted to be in this interval. Okay, so integral from 0 to 4 of 1 over 8 dx. Got it? So something really similar. Again, we get to factor out this guy, right? 1 over 8. We know that the integral with respect to x of 1 is going to be just x. So in the end, we're going to have just 4 minus 0, right? Let me write it down like that. So 4 minus 0, right? But that is just going to be 4 over 8, which is just 1/2. And that would be the expression we have for the marginal of y. No problem. Now that expression will be valid for y's that go from 0 to 2. And again, we have another continuous uniform distribution. Now this one in the interval, over the interval 0 to 2. Make sense? So both of them, both marginals by themselves, they are legit probability distributions. Okay? But now, we said that we wanted to talk about independence, right? So we have that the definition is, well, not the definition, this theorem that is going to allow us one way of showing independence is if we can express the joint as the product between the marginals, then the random variables in question are said to be independent. Okay, so in this case, note that the product of the marginals would be 1/2 times 1/4, and we have this, that they have to satisfy these two restrictions. X must be between 0 and 4, y between 0 and 2. Clearly, the product gives this, right? So since in this case, right, let's just say clearly the joint equals, oops, sorry, let me undo that. Let me rewrite that here. And let me copy paste this one here. That's better. Okay, so since the joint equals the product of the marginals, x and y are independent. Okay. So x and y are independent. Okay. Now, just as a homework problem, in this case, try and do this one using a different theorem from your textbook. Homework, okay. Homework. Try doing it. Well, this one, okay? This problem. Try doing this example using Theorem 5.5. Okay? Okay. So we're done with this example here. Let me show you another one. Let's try and do another one, and I'm going to be opening a new. Okay, great, because we're going to need some room. Okay. Let's try and do another example. Okay, but before I do that, let me show you something. So as you can see, this theorem has to do with continuous random variables. Okay. As you can see, there's a very similar way of showing that two discrete random variables are independent. The idea is the same. If you can express the joint probability function is the product of the marginals, then the random variables are independent. Okay? And this idea here, that if the joint is the product of the marginals, then the random variables are independent, can be extended to more than two random variables. Okay? Okay. So, let's do one more. Okay? You have seen that exercise before. You have seen that joint PDF before. Remember in another video when we talked about marginal density and conditional density, we talked about this same joint probability density function. Okay? So, let's use again the same theorem, the same result, to show whether or not these two random variables are independent. Okay? So we know that if we could express the joint as the product of the marginals, then the random variables in question are independent. Okay? So let's find the marginals. Guess what? It turns out that we have already found those marginals. As I said, we did it in another video when we discussed the concepts of marginal densities and conditional densities. So let me remind you what we had in that case. So we have the random variable f of x and y, if you will, equals 6 times 1 minus y2. Okay, if we wanted to use x instead of y1 and y instead of y2. Anyway, so that's the first marginal. Okay. So let me show you the joint. Another example. So what we have is f of y1 f of y2, and in that case we had 6 times 1 minus y2, right? And we need this guy to satisfy a few restrictions. let me go back to what we had the expression, where we had the expression, right? We have this. So y1 must be between 0 and 1, but must also satisfy an additional restriction. y1 must be less than or equal to y2, and y2 also lives between 0 and 1. Okay, and we have that the joint density function will be 0 elsewhere. Okay. Okay. So now, as I said, we had already talked about that marginal. Let me just remind you what we did. So just like before, by definition, we integrate with respect to the other variable, in this case y2, and what we ended up with was this: 3 times 1 minus y1 squared, and y1 lives in this interval 0, 1. Okay, so 3 times 1 minus y1 squared. So f, the marginal of y1, is just 3 times 1 minus y1, right, squared. Nice, huh? Between 0, 1. Well, in the interval 0, 1, right? And it's going to be 0 elsewhere. Okay. Okay. So we realized back then that, yeah, this marginal is a legit probability distribution, because this happens to be an example of a beta distribution. Okay, so this is marginal of y1. Okay. Now we have something similar for y2, right? What we have to do is just, since we want the other marginal, the marginal of y2, we integrate the joint PDF with respect to y1. Okay, so in that case, when we find that integral, we ended up with this expression here. Let me leave that expression like that instead of like this, because then from this expression here we can quickly see that the marginal of y2 happens to be another beta distribution. So it is a legit distribution in itself, a legit probability density function. Okay, so marginal of y2, let me copy paste this, it's going to be kind of useful. Now we have y2, 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 but now we said 6 times y, 2 times 1 minus y2, just y2. Okay, great. And y2 also lives between, well, in the interval 0, 1, and yeah, and it's going to be 0 elsewhere. Great. But now what we want to do is apply that theorem. So if the joint equals the product of the marginals, then we have that y1 and y2 are independent. Clearly, in this case, that is not satisfied, right? Can you see that? So let's just write that down. Since the joint is different from the product of the marginals, y1 and y2 are not independent. Oh, oops, independent. That's better. Okay, so just to summarize what we did in this video, we discussed the concept of independence, and there are different ways of showing independence between random variables. This is one way. If you can show that the joint PDF equals the product of the marginals, then your random variables are independent. And if that is not the case, well, then they are not. Okay. Please take a look at your textbook. For instance, Theorem 5.5 is another way of showing independence under particular conditions, particular circumstances. And yeah, that's it for now. Please keep working hard, take care of yourself, and see you next time. Bye.